Hello and welcome to a revision session from the Further Maths Support programme. Today we're going to be looking at Edexcel Mechanics 3, and this is the fourth part and last part of the Edexcel Mechanics 3 recordings. Today we're going to be looking at statics. Just to let you know that this is a four-part revision session. Today we're doing the statics side of this. If you're interested in revision for any of the other areas of the Mechanics 3 course, there are existing recordings for those as well. So first of all, we're going to take a look at the specification for statics. You need to be able to find the centre of mass of uniform rigid bodies and simple composite bodies. And you also need to be able to consider simple cases of the equilibrium of rigid bodies. Now, this is similar to the specification for M2 for statics, but we're adding in a couple of extra little issues here. So you may need to use integration to find the centre of mass of a uniform body, such as a solid of revolution, etc. And we're going to need to be able to consider situations where a rigid body is either suspended from a fixed point or placed on a horizontal or inclined plane, and we need to look at the critical values in those cases. So, very quick revision of the methods here. If we're talking about a composite body that's made up of recognisable shapes, then we calculate that we can say that the sum of the moments of the individual parts of that composite body is the same as the moment of the total solid about the same axis, and that's the fundamental method that we're using when we're calculating the location of a centre of mass. In the continuous version of the above, where you may have a shape that's defined perhaps by a function, then the integral of the moment of an individual element, so we take a small element of the whole shape and we find the moment of that individual element about a particular axis, and then we integrate that to sum all of those individual moments, and that will be equal to the moment of the total solid about the same axis. So if we know the mass or volume of the total solid, we can find its moment about an axis, and we make that equal to the sum of all of the individual moments. Okay, so we're going to have a go at a question here. If you want to pause the recording at this point and work through the question yourself, you're very welcome to do so, but I encourage you to pause it swiftly because I'm going to be starting on the solution. Now, if you'd like to just have a little read through the question here, a container is being formed by removing a right circular solid cone of height 4L from a uniform solid right circular cylinder of height 6L. To leave this sort of hollowed out shape remaining. We're going to find the distance of the centre of mass of this container from O, which is the centre of the plane face of the cone, and we're going to do this by setting up a table of values, and I strongly recommend using a table like this in the exam. It makes it much easier for the examiner to be able to see the methods that you're using at each stage, and to be able to ensure that you're given all of the marks that are due. So I'm going to list each of the parts of this solid, and then I'm going to put in the total for each one, and for each of the parts and the total I'm going to work out a mass, which is essentially an expression of the volume in each case. So the cylinder has volume pi r squared h, and in this case that's going to be pi times the radius, which is 2L squared, multiplied by the height, which is 6L, and we can simplify that down a bit to 24 pi L cubed. I'm also going to note that the distance of its centre of mass, so distance of centre of mass, C of M, from O, that's going to be given by 3L, half of the height of the cylinder, so by symmetry. Next I'm going to do this for the cone. The volume of a cone is a third pi r squared h, so in this case a third pi L squared, and then the height of the cone here is 4L. Now I'm actually going to make that negative, which seems like a strange thing to do, but because this cone is being removed from the system, its mass, if you like, counts kind of in the opposite direction from the mass of the cylinder. And if I simplify here, that's going to give me minus, oh sorry, that's not what I wanted to write. Let me just change that. Make sure it's tidy. So minus 4/3 pi L cubed gives you the volume of the cone. And the volume of the cone, the centre of mass of a cone, this is one of the standards that's on your formula sheet. For a solid cone, the centre of mass is a quarter of the way up the distance from the base, up the height from the base, so a quarter of 4L from O. So that's going to just give me, sorry, that's incorrect again. Sorry, I'm having a slight glitch here. Apologies. Talking and writing something different at the same time. Okay, a quarter of 4L, which is going to be L. We then need to put in the total, and 24 pi L cubed minus 4/3 pi L cubed gives me 68 pi L cubed over 3, and the distance of the centre of mass from O, I'm going to call that h bar. That's the distance that I'm looking for. Now, all of these volumes here are given in terms of pi L cubed. We're not really too bothered about the actual volume in each case. We're just looking really at the proportional volumes for each of them. So in my next calculation, I'm actually going to leave out the pi L cubed all the way through. But I'm getting ahead of myself. The next method is to take moments. So we're going to take moments about, and we need to define an axis. I'm going to say about a diameter through O. Okay, so we're choosing an axis across here. That's going to be the axis that I'm going to take moments about. So the cylinder's moment, I'm going to say, is 24 times 3L. Notice there I've eliminated the pi L cubed because I know it will cancel out in a minute anyway. The moment for the cone is going to be minus 4/3 times L. So again, eliminating the pi L cubed, and negative, as I say, because it's a space that's been removed, a mass that's been removed. That's going to be equal to 68 over 3 h bar. And if we do a little rearrangement on the fraction there, that's going to give me h is 53L over 17. Okay, we're going to go on to the second part of this same question. So we're now going on to the hanging and toppling topic. We have the container placed on a plane, which is an angle of theta to the horizontal, open face uppermost, as shown, and the plane is nice and rough, so it's not going to slip down the slope, but it is on the point of toppling over. Again, if you want to work through this question yourself, please do pause at this point. I'm going to draw some extra information onto the diagram. I'm going to draw in the axis of symmetry here. Actually, I'm going to do it as a line because my dotted lines are too scruffy. Now, if this object is on the point of toppling, it means that it's on the point of the centre of mass being below the lowest point on the of contact on the surface. Right, so that means the weight must be just acting through that lowest point. Okay, so here I've just put in W. The weight of the particle must be just acting through there, so the vertical that goes through this lowest point also goes through the centre of mass here. Now this diagram is not well scaled, but I think it should serve to work for us. So what we've got here now is we've formed a right-angled triangle. We know that this length across the bottom of the right-angled triangle here is 2L, the radius of the cylinder. We know this distance here is h bar. We just calculated that. We said h bar is 53L over 17. We worked that out in a previous part of the question. We know that the total height of the cylinder is 6L, so this section here, from here to here, is 6L minus 53L over 17. And that gives us enough information to be able to find out an angle in this right-angled triangle here. In actual fact, if we work this through, the angle made with the horizontal is theta, so this angle is 90 minus theta, so this angle is 90 minus theta, so this angle here is theta, and we now have enough information to be able to find theta. So tan theta, opposite over adjacent, that's 2L over 6L minus 53L over 17, which is a horrible clumsy fraction, but you can see there that the values of L are going to cancel away. We're left with 2 over 6 minus 53 over 17, which is about 0.6938, etc. And your calculator then can give you a value of theta, which is 34.75, and I'm going to round that just to 3 significant figures for the time being. So 34.8 degrees to 1 dp, or 3SF. Okay, so now we're going to take a look at a different type of question. Again, if you're working through this yourself, please pause at this point. I'm just going to skim read the question here. We have a region R bounded by a curve y equals e to the x, and these two lines x equals 1 and x equals 2. We're going to rotate that area around the x-axis through 2 pi to make a solid shape. I'm just going to draw in the other part of the profile of that shape. Please excuse my wobbly lines. So this is our solid. We have to show that the volume of S is given by the expression that's on the screen here. Okay, so let's be nice and precise. I'm going to select an element. Oh dear, sorry for the drawing. There's my element. Okay, and that element is a slice through the solid of revolution. So it's a disc shape. I'm going to say element is a disc. That disc has thickness delta x, so a tiny thickness that I'm going to make infinitesimal when I integrate. The radius of that disc is given by y, whatever the value of y happens to be at that point on the curve. The radius that gives the radius of the disc. So the volume of the disc is going to be given by pi y squared delta x. That's pi r squared, the circle area, multiplied by the thickness delta x. So if we want to find the total volume of S, we're going to have to integrate that. So total volume is the sum between 1 and 2 of all of those volumes, pi y squared, with respect to x. And we can substitute in for y there, so we've got pi e to the 2x dx. When we integrate that, we're going to end up with pi over 2 e to the 2x between 1 and 2, and we can substitute in our limits there, get pi over 2 e to the 4 minus e squared, and that was the expression that they asked for in the question. So far so pure. Okay, onwards then we're going to take a look at finding the x-coordinate of the centre of mass of S. Again, if you're wanting to work through this, now's a good time to pause. We're going to again think about our element. So the moment of our element, remember we were saying we needed to sum all the individual moments. So the moment of the element about the y-axis. Because we're looking for an x-coordinate of the centre of mass, we want to take moments about the y-axis. The moment of my element about the y-axis is its mass stroke volume, pi y squared delta x, multiplied by its distance from the axis, which is x. So pi x y squared delta x, or if you prefer, pi x e to the 2x delta x. So we can then sum all of those together. Total moment is going to be that integrated pi x e to the 2x with respect to x between 1 and 2. This is going to need integration by parts. We have a product of two functions, one of which is simplified when it's differentiated, and one of which doesn't get any worse when you integrate it. So using parts, u equals x, dv dx is e to the 2x. Differentiating, du dx is 1, and v is a half e to the 2x. So our integral becomes, I'm just going to take a factor of pi outside of the whole expression, pi times uv becomes x over 2 e to the 2x. Don't forget to put limits on that, between 1 and 2, minus the integral between 1 and 2 of v du dx. There we go. Close my final bracket there. So pi times, and putting our limits in here, when I put 2 in here I get 2 over 2, which is 1 e to the 4. When I put 1 in here I get a half e to the 2. When I integrate my half e to the 2x, I'm going to get a quarter e to the 2x between 1 and 2. Big bracket around the outside. And I'm just going to tidy all of that up. If you don't mind, this is just algebra, so I'm going to jump ahead a little bit on this one. That's going to give me an expression something along the lines of pi by 4. Bear with me just a second. 3e to the 4 minus e squared. I've just jumped a couple of stages there because they're just pure maths. Okay, so that's the total moment for all of the elements about the y-axis. So now I can equate my two total moments. I know that x bar times the volume, which we calculated in the first part, that's the moment of the whole object. That's going to be equal to the sum of the moments of all of the little objects. Sorry, pi by 4. 3e to the 4 minus e squared, and I can do a little cancel through by e squared, cancel through by pi, etc., and I should end up with x bar equals 3e squared minus 1 all over 2e squared minus 1. That gives my expression for the location of that position of that centre of mass. Okay, so that brings us to the end of our session. Thank you for watching. If you're interested in what the Further Maths Support Programme does, then I suggest a visit to www.furthermaths.org.uk, which is our home site. There are other recordings available for different modules in A-Level Maths and Further Maths. I hope you found them useful, and thank you for listening.